Hey, this is Horner, and this is the third video on what you absolutely have to know about fluids. So we are going to create a pressure in a piston full of gas. And so I have a cylinder of gas shown in the diagram to the right. The cylinder has a movable piston fitting on its top, and initially that piston, so here's the piston on top of the can. Initially, the piston is the top of the cylinder, and the pressure on the inside is 1 atmosphere. So it's just sitting there. We also, remember, have pressure pushing down. So we've got 1 atmosphere pressing down, and we have 1 atmosphere pressing up. So we would say that this is a neutral situation. Nothing's going anywhere. Um, if I take a zero point 0.4 kilogram mass and I put it on top of it, obviously it compresses that gas and it's now a much smaller volume. So they want to know, what is the new pressure in the gas? To define that new pressure in the gas, we've got to do a few things. Let's do a free body diagram first. We have our piston, and on top of it we have our box. So there's our box on top of the piston. We know that for the box, we have, here, let's change colors. For the box, we have mg pointing straight down. We know that we have the force of the gas pointing straight up. And we also have the force of the atmosphere, so we'll just put ATM right there. So that's our free body diagram. The other thing we need to do is we have an area here. So the area is equal to, I think I lost my pen here. Area is equal to, and you'll notice that there's an error here. It says 200 cubic centimeters. It should be 200 square meters. So area here is equal to 200 centimeters squared. And I need to get that to meters squared, so that'd be 100 squared centimeter squared, 1 squared meter squared. If you don't put the square on everything, it won't work out right. So you'll get 0.02 square meters here. So let's go through and let's do some of the forces. Because it's not accelerating, we're going to say that's at 0. So we have the force of the atmosphere plus the force due to gravity, and that would be equal to the force of the gas pushing back up. And it's because really what we've done here is I've skipped a step. I probably should have said force of the atmosphere plus mg minus the force of the gas is equal to 0, and then that gets moved to the other side. The force of the atmosphere, well, they really didn't tell us what it is, but we know that we have the pressure of the atmosphere, and if I take that times the area of the lid, pressure times area is a force, because remember, pressure is equal to force per unit area. So that makes force equal to pressure times area. So that's P times A plus mg, and that's equal to the pressure of the gas times the area that that gas is acting on. So this is the atmospheric pressure, ATM. We get about 100,000 for this value for pressure. Area is 0.02 plus, and then we've got 0.4 times about 10, and that's equal to the pressure of the gas times that 0.02 square centimeters, sorry, the 0.02 square meters again. So when you're done, you should end up with a pressure in the gas equal to 100,200 pascals. So that is the how you do that problem. Let's go ahead and take a look at the next one. This is called Pascal's principle. So it says, speaking of pistons, there's another great property of fluids. If you take an external pressure applied to any point of a confined fluid, so notice that it's not open to the atmosphere anywhere, the pressure, that increases the pressure everywhere in the fluid. So if I have a mass added to the piston in the figure above, so when we were talking about this guy, I know that the extra pressure it applies to the gas happens in the whole thing. So if the pressure goes up everywhere in the gas, it goes up by the same amount, and we call that Pascal's principle. So it's a really important thing. We can put this into use in something called hydraulics, liquid devices, and pneumatics, which is a gas device. And in the figure here that we see, we have a couple of different size cylinders. When I put F1, put a pressure on it, it then pushes down into the tube, and the fluid gets pushed over and then pushes this side up. Okay, the extra pressure applied to the left cylinder is transmitted to the right cylinder, and that creates a force pushing this up. Now, if I look closer, I see that the area of A2 is bigger than A1. And so we can use the ratios of the two to figure out kind of how much it will multiply our ratio. So when I push down here, I don't need as much force to lift something very large. So the device magically seems to increase our force, and it violates then the conservation of energy, which would be really bad. Explain why this device really doesn't break any physics rules. So while hydraulics and pneumatics are great devices that increase the force output, the work output of the device is no greater than the work in. So when the smaller left cylinder gets pushed down, okay, only by a small amount of fluid moves to the right cylinder. So you don't get a lot, you get a little bit. Therefore, the right cylinder moves up just a little bit less than the left cylinder does. So this one's probably going to need to move down all the way here for this thing to move from its original spot here up to where it is now. So there's not a lot here. So work input, the force times distance for the left cylinder is just as big as the work output for the other one, because here our force is small, but our distance is really big. And over on this side, our force is really big, but the distance we moved it is really small. Same principle applies if you've ever had to change a tire on your car and you have to jack the car up. You have to actually work that jack a lot up and down in order to get the car to move up hardly at all. And that's what you'll see. This is the end of this page, and the next page has a different topic, so we'll stop here and move on with the next one.